So the first one is let's talk about okay. Can you see my screen?
Cannot see, sir.
Why? I share already. Can you see?
Check.
You okay, right? Yeah. Okay. So basically, we so-called analog signal conditioning, and then we will look at digital signal conditioning. So why do we need to try to find a way so that if I press the erase button, you can also see it. Okay, so why we need to look at signal conditioning? It is because the typical arrangement or structure of the measurement system is this is what you want to measure, right? What you want to measure is something may not be electrical, right? It can be temperature, it can be humidity. Then you have a sensor, and this sensor will provide you with a range of uh, the sensor will provide you with an electrical signal. It can be in the form of voltage, it can be in form of current, it can be in form of varying resistance or capacitance. However, this is not the end of the story. In the whole system, you may have other parts as well working together. So when you combine or you want to link one portion of the whole system to another portion of the whole system, there may be mismatch between input, output here, and some input to the next part of the system. Then you need to have this kind of signal conditioning, right? So in terms of definition, signal conditioning basically are all the operation you can perform on the signal. And then you can convert, right? You can convert to a form which is suitable for interfacing with other elements, right? So sometimes you may want to remove noise, so that's why you, right? And maybe you want to amplify the signal, that's why you have to have amplifier. Sometimes you need to change the range, right? So suppose the signal here is from like -1 to 1, but you want to convert it to from like 0 to 10. So those are the circuit um, performing the operation to fit, right? To transform the signal from one form to the next form, right, suitable for interfacing. Okay. Nowadays, we use digital computers a lot. However, not everything is done digitally. We still need to look at some example in analog domain. So that's why we come to this part of the lecture. Now, let's take a look at some examples of what you can do in terms of signal conditioning in analog domain. Now, here, you need to change the signal level and bias. So here's one example, right? So suppose you have a sensor, and this sensor provide you with a voltage from 0.2 to 0.6. But you have this is another circuit, right? Another circuit. But this circuit, they want to have a voltage from 0 volt to 5 volt, right? So somehow you have to 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 convert this range to this range. How to do so? First step is you may want to bring everything down, for example, to 0 volt to 0.4 volt. So from here to here, right, you minus 0.2. All right, you minus 0.2 to have 0 to 0.4. And then from here, if I multiply with 12, right, so you see 12 times 0.4 is 5, and 12 times 0 is 0. So I need to do two things, right? I need to bring down the level of the voltage here down to 0 to 0.4. Then I need to do amplification, right? So the signal conditioning portion must perform these two for me, right? 0.2 to 0.6. So the signal conditioning must do these two operations for me. So this is very common example. So we have to design circuit in such a way the circuit can subtract minus 0.2 volt and then amplify by 12 amps. So that's one example. Then another example can be focal linearization. So why you want to have this kind of linearization? It is because if it is a linear one, then from the voltage you measure, you can easily, right? You can easily calculate it. What is the input values, right? So sometimes the curve is not so linear. Then you must have some linearization circuit to help you with the calculation. Right? Conversion, right? So you have to convert one type to another type. So sometimes we need to convert voltage to current, then current to voltage. Now, why? Just one example. So suppose this is your factory, for example, and then you need to transmit the signal by wire quite far away to a center, right? So at this point, for example, you have voltage. Then if you use voltage and you transmit voltage over a long distance, the voltage will be attenuated. But if you have current, then the current will not be attenuated. So you have to convert from voltage to current, and the current can flow into a long distance. And at this point, you must have a current to voltage converter. So at this point, you still have what you can measure here, right? So that is one example of sometimes you have to voltage to current, current to voltage. Then you may need to do filtering to remove some noise in your signal or to do impedance matching. So those are some examples of what you have to do in analog domain in instrumentation system. Another problems you may have when you combine different subsystems together is so-called loading problems. Loading problems. So loading problems. So I think this will be easier to understand if you come back here and look at the one example, right? So suppose you have a sensor. You have a sensor. And this sensor can provide you with the voltage Vx if you have the open circuit here. So suppose you don't have this part of, so this one is another subsystem, right? This one is another subsystem. Suppose you don't have this subsystem, you measure the open open circuit, the voltage over these 2 points, you should have Vx. And then Rx doesn't matter because you measure the open circuit, right? Correct? But suppose you have to link the system, the second subsystem here, and link to the sensor. Now, all the sensor have internal resistance. And this one in DC modules, I think in the second semester, first year, right? You also learn about Thevenin equivalent, right? So you have a source here and then you have internal resistance here. Then the voltage you can get by the second subsystem is not Vx anymore. So the voltage you have here is called Vy. This is a voltage the second subsystem can get from the first subsystem, which is a sensor. It is not Vx anymore. Why it is not Vx? Because you have two resistors in series, and then you have to apply the voltage divider rule, right? So the voltage divider rule tell you that Vy is RL over RL plus Rx times Vx, right? So you don't have Vx totally, right? But you have some voltage drop over Rx. Right? Okay, but there's one observation here. Suppose your RL is much bigger than Rx. RL is much bigger than Rx. This one. So if RL is much bigger than Rx, I can forget about this Rx. Then this one is become Vx, right? Okay, so the second subsystem should have a very high input impedance. So if the second subsystem has very high input impedance, then the voltage the second subsystem get should be the same as this guy, right? So that is the explanation of the loading problem. Right, so here's another example. Suppose you have a temperature sensor and you have 20 millivolt per degree Celsius. So if the temperature here is 50 degrees Celsius, then the voltage you get at this point should be 50 times 20. So 50 times 20, which is 1 volt. And imagine you have a amplifier with a gain of 10. So you expect this VL should be 10 times 1, which is 10 volt. But the problem is more complicated, because if this amplifier has a low input impedance, so suppose this guy is 10 kilo ohm, the input impedance of this guy 10 kilo ohm. So you will see, right? The voltage here you have is 1 volt, but this 5K and this 10K are in series. 5K is the internal resistance of the sensor. So the voltage you get here is 10 over 10 plus 5 times 1, which is 10 over 15, which is 2 over 3. 2 over 3 is nothing but just 0.67. So we cannot get the full 1 volt here, right? You cannot get the full 1 volt. Now, after you have 0.67 to this amplifier, if you amplify by 10 times, the voltage you get is only about 6.7 volt. So you don't have this 10 volt. So loading is one serious problems when you combine multiple subsystems together. Okay, so that's why you see you learn quite a lot of op-amp circuit, right? Because one characteristics of op-amp is the input impedance is very high, right? So you can use that op-amp to interface to build interfacing between multiple subsystems. So that is the one part to introducing the analog signal conditioning. Now let's look at the typical example of circuits in analog signal conditioning. Right. Now the first part is we're looking at the passive circuit. So for passive, I think you have learned it in other modules as well. We are looking at the circuits of R, L, and C, right? So when we talk about active circuit, the typical example is the op-amp lah, right? Op-amp. Okay. Now, so we are looking at the bridge, and also another one is filtering. Okay. So let's take a look at the some other example as well. This one called divider circuit. Right. Divider circuit is basically to change one level of voltage to another level of voltage. So suppose this one is too high, you want to reduce it, then you can make use of this divider circuit. The divider circuit is nothing but just a voltage divider, right? So the formula is R2 over R1 plus R2 times PS. Correct? Then there's some problem with this circuit. Number one is output impedance is R1 parallel with R2. So I think this one you have seen it in your DC modules, right? When we talk about Thevenin equivalent. When we talk about Thevenin equivalent, so this one is like it become here is VD, and this one is R1 parallel with R2, something like this. Something like this. And also is talk about power consumption, because when you have VS here, so the current flow down here, so you have power dissipated on this. What's wrong? What is this? How come? So for example, you have VS here. VS here, so there's a current running down. So power is dissipated here. Right? Okay, that is another example. Now the bridge circuit, I think you have seen it before. So I won't go through much detail on how to derive this. Basically, you have a voltage V here. Then you have R1, R2, R3, R4, and this is point A and B. You try to determine what is VAB. Right? So the delta V here is nothing but just VAB. So to determine VA and to determine VB is nothing but just voltage divider rule. And to determine VAB, you just take VA minus VB. VA minus VB. And once you have this, then this is a formula. Of course, the bridge is called balance. This one is bridge is balance. If you have this product, right? And then the delta V is equal to 0. All right. Now this one will be used in, for example, when we talk about sensors based on varying resistance, we will fix. So suppose R1, R2, R3 are fixed. And in this case, it's fixed at 100 ohm, for example. Then R4 will be changing, right? R4 is changing. So from this formula, if you put in all the R1, R2, R3 values, then you can have this one. Correct. So it is something like if you have a varying R4, then after this one, you have delta V. But delta V is nothing but just VAB, right? So after you have this equation, if you plot it over here, you will have a curve like this. So when R4 is changing, then your delta V is also changing. Now, if you will have 0, the delta V or VAB should be 0 when the R4 also 100 ohm. So if you look around this small region, you can have something like this. So this one is similar to a straight line, right? It's look very much similar to a straight line. So for this straight line, if you can measure the delta V very easily, you can determine what is the R4. And of course, R4, the variation of R4 is the results of some quantity you want to measure, right? So this is the example of how from measuring VAB, you can determine the quantity you want to measure here. Okay, so that is another example. Now, of course, filtering is very important operation in the circuit because you may need to remove some noises from your signal. Right. So here is something you have seen it before, but I just have some recap here in case you already forget. So the signal you are dealing with consists of what you want and also the noise coming from all sorts of interference. Right? So when you add what the signal you want and the noise you have, so this is the signal and noise. To quantify the strength between the signal and the noise, we are talking about SNR. So this one is signal to noise ratio. So if the signal to noise ratio is high, it means your signal is much stronger than the noise. So even when you add the signal and the noise together, you can still see the shape of the signal. But when the signal to noise ratio is small, that means the signal does not so strong as compared to the noise. When you add them, basically you can't see the signal anymore, right? Of course, in the system, we want to have a high signal to noise ratio. So how to measure the signal to noise ratio? You need to look at the power of the signal, the over to the power of noise. And take note for this one is no unit, right? Because here is watt over watt. It should be no unit. Now, normally in engineering, we will have the SNR in dB. So in dB, basically you calculate this formula 10 to the power of log of the P signal over P naught. So this one is in dB. Okay. So suppose if you have 10 dB, signal to noise is 10 dB. What does that mean? It means, so how to have 10? So it should be 10 times 1, right? 10 times 1. And this one is log space 10. So in order to have 10 dB, this one must be 10 times. So the signal power should be 10 times the noise power. Now, if you have 20 dB, this one should be 100. So the signal power should be 100 times the noise power. Then you have 20 dB. Okay. You can also calculate it based on, for example, here if you convert power to dB, then the SNR in dB is signal power in dB minus the noise power in dB. Correct. Then please do not confuse between dB and dBm. Because Sean can enter. Please do not confuse dB and dBm. So for dBm, this one is referred to power. This is a unit of power, right? It's a unit of power. So for example, if you have power, you convert this one to milliwatt, and then you plug in this formula, the result is dBm. Right, so dBm is a unit of power. Okay. Right. Now, if you have voltages, then you can make use of this formula to calculate SNR in terms of voltage. Now, why this one is 20 is very simple. Previously, you see power signal over power noise, right? But power of signal should be proportional to square of the voltage of the signal, and the power of noise should be proportional to the square of the voltage of the noise. And this one should be 10 log Vs over Vn square. Right? And this one become, if you bring the 2 down here, you should have 20 log of Vs over Vn. Right? So that's why you can calculate SNR in terms of voltages. Okay, so here is some example. Now the signal, the power of the signal is 10 watt. So P signal 10 watt. And the power of the noise, this one is power of noise. So they ask what is a SNR? So it's very simple, right? 10 watt will become 10,000 milliwatt. And the noise is 1 milliwatt, so the SNR is 10,000. But if you want to change the dB, then you just plug in the value here. So we have 10 log base 10 of 10 to the power 4. The 4, you can bring it outside. So we have 40. This one is 40 dB. Okay? The next simple question is, suppose the power is minus 30 dBm. What is the power in milliwatt? So how to calculate dBm? dBm is 10 times log base 10 of the power. This one must be in milliwatt. Right? I have minus 30. So if I have minus 30, then I divide by 10. So log base 10 of PM should be minus 3. And PM should be 10 to the power minus 3. So it's very small, right? This one is very small. So that is a few simple example. Here is some example of sources of noise. You can just take a look. And how to do noise prevention. You may want to have, for example, twisted pair to reduce the noise. Also, shielding, right? So basically, you have some shielding to cover the signal wire. Right? And another one is, for example, then you may want to have a filter as well. So let's take a look at some example of filters. This one, just a recap actually, because you have seen these kinds of circuit in previous modules. And by the way, next week we have quiz, right? So one part of the quiz should be on this. Okay. So to make it simple. Another part of the quiz should be on reliability. Okay, so that is another. Okay, so we will look at the passive one which consists of only R, L, and C. And we will look at active one, which consists of op-amp together with normally is R and C. Why they don't use L? Because L is quite bulky. Inductor is quite bulky. Capacitor is more compact and the size is very small. Okay, so that's why. Now let's take a look at the filters. You have 4 kinds of filters. You have low pass, high pass, band pass, and band stop. This one is just to show you the visualization. I draw like this is to say for the input, right? You have all frequencies. All frequencies you have here at the input. But if you use the low pass filter, then only low frequency is can pass. Then the high frequency is killed off or is removed, right? If you look at high pass, then high frequency survive, low frequency is removed. Band stop is when you kill a band here, right? You keep from this band and this band. Band part is you preserve a small band and then you kill the low frequencies. Also, you kill the high frequency. Okay. Okay. Right. When you look at the filters, then filter can be considered as a system where have input and output. And for a filter, you can have the gain. The gain is just a ratio of output to the voltage, output voltage to the input voltage. And for this gain, if you convert to dB, and because here are voltages, so you can convert to dB by using 20 times log base 10, right? Of course, if you have the values in dB, you can always convert to non-unit, right? So this one is non-unit because you have voltage over voltage, right? Okay. Okay. So that is. Now, for all the filters, you have the so-called frequency response. Okay, you have frequency response. This one is to show you what is the gain at different frequency values. So for the low pass filter, this is a shape of the frequency response, and this one is gain, right? This axis is gain, right? This is a band pass, and so on and so forth. Right. So up to this point, you will see you have 2 different bands, right? The first part here is band pass, and this one is band stop, right? It will have later on we will go into a bit of detail of the minus dB1. Okay, the minus dB1 or the half power frequency here. But basically, if you have the top gain and if you bring down to 3 dB, so you go down 3 dB from the top. You go down 3 dB from the top, you will have the boundary between passband and stop band. And this one is called cutoff frequency, right? Those are the things I think you have seen it before. Okay. So let's take a look at the cutoff frequency. So this is, for example, this is a max, and you bring down to 3 dB. So imagine if the max gain here is 1, and if you have the max gain 1, it means you have here is 0 dB, right? So the gain is 1, then it is 0 dB. Why 0? Because 20 times log base 10 of 1, which give you 20 times 0, which give you 0 dB. Right? Now, if you go down to minus 3 dB, basically you go down to 1 over square root of 2, the max. Okay, now why 1 over square root of 2? It is because if you have 20 times log base 10 of 1 over square root of 2, this one similar to 20 log base 10 of 2 minus half. And this one, it become 20 times minus half times log base 2 base 10 of 2. Or you have, if you have a calculator, you can just use a calculator and determine this value. This one should be 3 dB, right? So if you go down to 1 over square root of 2, then V out over V in is also 1 over square root of 2. Correct? And because here is a ratio in voltage, then if you have the ratio in powers, then you can square this ratio, then you have half. So that is the reason why the cutoff frequency has another name. It's called half power frequency. So in this particular frequency, if your input power is for example, is 1 watt, then at this the output power is only 0.5. Right? So for example, at FC here, the power is 1 watt. So after going through the filter, you still have the frequency FC, but the power here is only 0.5 watt. So that's why it's called the half power frequency. Right. So here is the first order low pass filter, right? And passive lah. So you have R and C. Now, I think you have seen this many times already, but to look at how come this one can allow the low frequency to go through, you can think of 1 over omega C. This guy has 1 over omega C. So when omega is small, right, then this one is big. Correct. So V out is big. But if if omega is big, it means you have high frequency, then 1 over omega C is very small, right? Very small, for example, very small. So the V out here is disappeared. Right? So that's why you have it here. And the cutoff frequency, I think you have seen it before, is 1 over 2 pi C. Right? So this another way to look at the gain, and here I convert to dB. So this, if the gain in terms of voltages is 1, this one is the point here when the dB is 0. Okay. This is a first order high pass filter. I think you have seen it before, right? You just need to swap the order of R and C. The cutoff frequency is still 1 over 2 pi RC. Right, so this is another way to look at the high pass filter if I convert the gain to dB. So the shape look like this. The roll-off rate, what does that mean? It means if you, so here, this one means if you increase the power by 10 times, then the gain is dropped by minus 20 dB. So it's minus 3. No, sorry, this one is not. So suppose you look here, it will bring down to minus 20 dB here. So if you go another 100 FC, right? So if you are at 100 FC, so basically you go another minus 20, so it should be at minus 40 dB. That's what it means by the roll-off rate. Right? Decay is 10 times 10. So I think this one you have seen it in other subjects as well. Okay. Now, how to have a band pass? You combine low pass and high pass. Right. So, for example, this one is your low pass filter, right? This one is your high pass filter, right? So when you combine, you have this shape, which is a band pass filter. Then you have FC1 and you have FC2. Two cutoff frequency, and the center frequency is calculated in this way, right? And for bandpass filter, you have a Q factor. So Q factor is a ratio of the center frequency over the bandwidth. And if it is more than 10, this one is a narrow bandpass filter. And if it is small, then it is a wide bandpass filter. Okay. Now, I have one question for you. This guy coming from where? Coming from low pass filter or high pass filter? Same thing. The FC1 and the FC2, they're coming from which filter? FC1 is a cutoff frequency of which filter, and FC2 is cutoff frequency of what? Which filter?
Low pass filter.
Which one? FC1 is low pass.
FC1 low pass. Eh?
I don't think so.
FC1 high pass.
Yeah, FC1 must be high pass. It is because, right, you can think of this as two process. After, so the first step is the signal pass through the low pass, right? It means you keep like this, right? After it pass through the low pass, you keep the signal like this. So here you have one like FC, correct? And for the high pass, right, it should be something like this, right? This one. This one should be the high pass one. So to remove some frequency here, right? So this FC must come from the high pass. So FC1 must come from high pass. And FC2 is here, must come from the low pass filter, right? So that is some example. Okay. Okay, so I think we can have a short break, and then I will move on to the next part. Let me share the QR code again. Yep, if you can. Yes. Okay, please scan the QR code. Okay. Let's continue. So we will look at some circuits using op-amp that help us to do all kinds of operation you want to have. Right? Can be form filters. You can amplify the signal if you want. You can adjust the level of the signal. Later on, we have all the example like that. Or you want to separate between this subsystem to another subsystem, then you can use buffer. So the thing is, all this you have learned before. Okay, so here it's just like, because it's quite some time already, so some of you may already forget. And we look at op-amp in the combination with other elements to form the whole circuit, the whole system. Okay. So this few slide here is just to remind you, op-amp has two input terminals, inverting and non-inverting, and it has one output. Op-amp is an active element because it can provide you with gain. In the passive circuit, you cannot have gain. You can't amplify the signal. How come the op-amp can amplify the signal? It is because op-amp is powered up by external voltages, V plus and V minus, or sometimes you see VCC and minus VCC, right? So these external voltage sources are helping the op-amp here to amplify the signal. Now, op-amp has input impedance and output impedance, Ri and R0. The output of op-amp is very simple. It is A times VD. And what is VD? VD is here. So it's V2 minus V1. So the V2 here is a non-inverting terminal, and V1 is the inverting terminal. So if you have a voltage between the two terminals, you multiply with A, then you amplify it. Now, normally for voltage, right, you see the, you have a, in terms of schematic, you have a circle. But this one is not a circle, this one is a diamond. Why it does so? Because for circle, this one is a rotation of independent voltage source. Like battery is independent, right? Or the power bank we have. After you charge it, then it becomes an independent voltage source. The diamond here is stand for dependent voltage source. Why is dependent? Because, yeah, right, the value we control by this guy, VD as well. So it's A times VD. So when VD change, this V also change. Right, so this one is a dependent voltage. Normally A is huge. A is very huge. And you are capped at VC and minus VCC. So if the input volt, the VCC is 10 volt, then the output cannot be above 10 volt, right? So normally we don't use op-amp without the feedback, right? Because the output will be saturated very quickly. Okay, as long as you have a small difference between V2 and V1, the output voltage become either VCC or minus VCC, right? So you should have the feedback in op-amp circuit. When we analyze and when we design op-amp circuit, we have these assumptions. We use this assumption the gain is infinite. The input input impedance is infinite, and the output impedance is 0. So this one you have a very high input impedance, right? Okay. Now, if you base on this assumption, when you analyze op-amp, you must remember these two things. The first thing is there's no current running into the terminals because Ri here is infinity, right? So there's no current running into this, and also the voltage of the two terminals must be the same. Right? So V2 and V1 must be the same. So because V2 and V1, they are the same, so there's no current running through here, right? Because if they are different, then there should be some current, right? So this you must remember when you if you have to analyze any op-amp circuit. So take note of this. Now, if you want to amplify the signal, you can use inverting amplifier or non-inverting amplifier. So this is a so-called inverting amplifier. Why is called inverting? Because the VI here is the one you want to amplify. And this one will basically link to the inverting terminal, right? And later on, you'll see the gain is also minus. So have you seen this one before? Of course, you have seen this one before. But here I just want to show you a little bit of recap a bit on the analysis of this. Right. So look here, the V2 should be 0 volt, right? Why volt? Because you link to the ground. Because V2 is 0, so V2 is 0 volt because it's linked to the ground. Now V1 must also be 0 because voltages at the two terminals are the same. So that's why the V1 here should also be 0. This one also be 0. So this is a case where we say we have virtual ground, right? Remember? Virtual ground. Because this point does not link to the ground by wire, but the voltage at this point is 0. So it's called a virtual ground. To determine the gain of this circuit is very simple because you look at this point, to this point, the voltage should be VI, right? So the voltage at this point should be VI, right? Then it's go through R1, right? Then it's go to 0 volt, right? This point is 0 volt, right? Then it's go to RF, right? This one. Then it's go to V out. Why I don't care about this wire? Why this one gone? Because based on the op-amp here, there's no current running into the two terminals, right? So if there's no current running here, basically, makes sense, right? Okay. So here's V0. So now if you have the I1 here, and you have the I2 here. So I1 is very simple. It is V input minus 0 over R1, which is V input over R1. And for I2 is 0 minus V out over Rm. So this one is minus V out over Rm, right? Now I1 flow in, I2 flow out. So I1 and I2 must be the same, right? So I1 must be the same as I2. So Vi over R1 should be the same as minus V out over Rf. So if this is the case, then your V out is minus Rf over R1 Vi. All right, like this. Right, so because of the minus sign here, then it's called the inverting. Right? This one we call the inverting. Because if VI is positive, then VO is negative. VI is negative, then VO becomes positive. So that's why. Okay. So this is a inverting amplifier. So if we need to amplify the signal, you can use this one. Right. So so here is one example. So this one is VI, which is 0.5 volt. This actually is our RIZ. This actually is our RF, right? So your VO is minus RF over RI times VI. So this one is minus 25 times 10 times 0.5. So it's 0.5, 0.5. Correct? Right? Okay. And if they ask what is the current in 10 kilo ohm, so suppose they ask what it is I. So take note, this point, the voltage is 0 volt because you link to the ground. Therefore, at this point, the voltage must also be 0. Right? So again, at this point, the voltage is 0.5 volt. So here is 0.5 volt. This end is 0 volt. Right? So the Ohm law, you can apply Ohm law here. So the Ohm law tells you this I should be 0.5 minus 0 over 10 kilo ohm, right? So this one is 0.05 milliampere, right? So I think this one is just a simple one. Simple one about amplifier. Now let's take a look at the second example. This one is just to highlight to you that you cannot apply formula all the time. Okay? You can't apply formula all the time. This formula is only applicable for this circuit where the minus terminal, the plus terminal is linked to the ground. Now imagine in this case, if you have this a bit of change, then how are you going to handle it? Maybe I give you a few minutes. Now, what is the voltage at this point?
2 volt.
Yeah, 2 volt. Therefore, the voltage at this point must also be 2
volt.
volt, right?
Yes.
Yeah. Correct. And you don't have the current running into the terminal, so you can forget about this. What is the voltage at this point?
6 volt.
Yeah, 6 volt. So you can actually have a very simple circuit. Here, this point you have 6 volt. This point you have 20K. Going to 2 volt, right? Because that is a point A here. From A, I go to 40K to be out. So I go to 40K. Here we are. Now imagine if I have here is I1 and here is I2, for example, I change the direction a bit. So the I1 is nothing but just 6 minus 2, 6 over 20 kilo. So you have 4 volt over 20 kilo. So here you have 0.2 milliampere, right?
Yes.
And your I2 should be Vout minus 2 over 40 milliampere. This one is milliampere. Then what happened to I1 and I2? Are they the same? If I write I1 equal I2, is it correct?
Correct.
No. I1 entering, I2 also entering. So I1 plus I2 is 0. ACL, right? Entering, this one also entering. So from here, your I2 should be minus I1. Let me write smaller, otherwise I don't have enough space. I1 plus I2 should be 0. From here, your I2 is minus I1. So you have V2 minus 2 over 40 should be minus 0.2. Should be minus 0.2. So you have VO minus 2 is minus 8. Correct? Yeah, minus 8. So your VO is minus S plus 2 is minus 6. So you can't always apply the formula, because if you apply the formula blindly, then you may say, oh, it's 40 over 20 times 6, which is minus 12 volt. But this one is wrong. So it's here. Then you have a non-inverting amplifier, right? So the non-inverting amplifier, I think I just give you the formula, because VO is 1 plus RF over RI times VE, right? And by the way, this one is a good one because the input impedance is very high. Input impedance is very high. No current running here. So imagine if here you have internal resistance, right? So suppose this one is your sensor. This one is your sensor with a input impedance here. Oh, no, internal impedance. So when you connect like this, there's no current running here because the input impedance is very high, right? So you can get the full VI, right? You can get the full VI here, and then you can amplify. So this one, I think you learned is before, okay? If you want to know how to prove it, you can ask me. Now let's take a look at this example. So this one, same for the like the previous case. At this point, you should have 4 volt, right? And at this point, you should also have 4 volts, right? And at this point, you have 6 volts, right? So again, here you have 6 volts. Here you have 4K. Here you have 4 volts. Here you have 10K. Here you have BR. So let me do it a bit quickly. This current is 6 minus 4 over 4 milliampere. Should be the same as. So now it is, if I have the current like this, then I1 and I2 are the same. It's different from this case where I have I1, I2 opposite, and I1 plus I2 is 0. So this one should be 4 minus VR over 10. So 4 volt minus VR over 10K. And because here is kilo ohm, here also kilo ohm, so milliampere, milliampere. Right? So this one is 2 over 4 is 4 minus VR over 10. In other words, 4 minus VR is 10 times 2 over 4, which is 5, right? So VR is 4 minus 5 is minus 1. So just something I believe you see it before. Not totally new, right?
Yes.
Now this one a bit tricky, a bit tough. Can you try? So this one, you can think this way a bit. So now there's no wire running. You can think of it as not having this wire because there's no current here, right? So can you tell me what happened to this 4K and 8K if you don't have the wire here? What happened?
Series.
Yeah, they're in series, right? So suppose I call this one is V1. So V1 is nothing but just a voltage on this 8K, right? Okay. So V1 is 8 over 4 plus 8, right?
2 volt.
So times 3, 8
Volt.
over 12, 3,
3.
2 volt, right?
Yeah.
If that is the case, then this V2 must be V1 must be 2 volt as well. Because the voltage at the two terminal must be the same. And also, you can think of not having this wire because there's no current running. Handling this circuit is quite simple because you can straighten the circuit. Here you have VL. It should go down through 5K to V2. So it's go down through 5K to V2, which is 2 volt. Then from 2 volt, it's go down to 2 kilo ohm, go to the ground.
0.
Right? Yeah. So how to find VL? Actually, it's quite simple. There's multiple way. There's multiple way. Look, what is the voltage across this 2K? If here is VL, it's 2 over 5 plus 2 times VL, right? It's a voltage divider rule, right? The voltage across this 2K should be 2 over 2 plus 5 times VL. But this voltage is already 2 volts due to the characteristics of the op-amp. So this one is 2 volts. So here we have 2 VL over 7 with 2 VL. 2 VL is 14. VL should be 7. Right? That's how we can. So actually, if you apply the characteristics of op-amp when you analyze, quite simple. Right? Now, if you want to separate between different stages, so this is one subsystem, this is another subsystem, we want to avoid the loading problem. In between, you can use a voltage buffer or voltage follower, right? So what is the characteristic of the voltage follower? Number one, the input impedance is very high. So you basically don't have the current running into the wire. So at this point, you should have VI, right? Total VI. And because of the characteristic of the op-amp, the two terminals must have the same voltage. So at this point, the voltage also VI. And here also VI, here also VI, here also VI. So the voltage entering the second stage is actually VI. Right?
Yes.
So if you have a buffer like this, you can avoid the loading problem. You can avoid the loading problem. So here again, look at this example. Imagine if you have a sensor where the input impedance of the sensor is quite high, 10 kilo ohm, and the sensor can provide 11 volt if you have open circuit. And now imagine if you plug it into a sub-circuit, all right, subsequent subsystem where the input impedance is 1K, then the voltage you get for this guy is only 1 over 11 times 11, which is only 1 volt. And 1 volt is only about 9% of this 11 volt. How to cure the problem? You have a buffer in between. Yeah, buffer in between. So when you have a buffer in between, there's no current entering the buffer because the input impedance of the op-amp is super high. And because of that, the VA here should be the same as 11 volt because there's no current, so there's no voltage drop over the 10 kilo ohm. So we have full here is 11 volt. And because this one is 11 volt, so the VB also 11 volt. VB also 11 volt. And this 11 volt come to here, 11 volt. So now you have full 11 volt to the load, right? So that is the benefit of having a buffer. This one is another example. Right, you have 3 volt, 3 volt. Okay. Then if you have a buffer like this, basically there's no current running into here. So this 8K and this 8K, you form a voltage divider. So the V here is 1.5. So at this point, you have 1.5 volt. All right. Then this point, you also have 1.5. And because you have a wire here, so now at this point, you have 1.5 volt. And because this is the inverting amplifier. This one is inverting amplifier. So you have 1.5 volt here. The formula is minus 50K over 10K times 1.5. You have minus 7.5. Right? Minus 7.5. Okay. If you don't have the buffer, then the scenario is different. Why? Because look at this. This one can be Thevenin, can be converted to 1.5 and 8 parallel with 8. We have 4K. Then it's linked to this 10K, right? And linked to this. $50K. Then the voltage at this point is not 1.5 anymore. It's not. It's not like here you have 1.5 here and then you have B5. Now why? It's very simple. This is a ground. So here is also 0 volt. So you can think of this as virtual ground, right? Right. So basically 1.5 volt here is used to provide current running through 4K and 10K. So the voltage at this point is 10 over 10 plus 4 times 1.5. So this one, of course, less than 1.5. Right? Because here you think of, here I have 1.5 through 4K, through 10K go to ground. So the voltage from here is calculated by this. Right, so without the buffer, you cannot have 1.5 volt coming from the point A. Right? So this one is just to show you the benefit of having the buffer to separate from this subsystem to this subsystem. Okay, so that is now the summing amplifier. This one will be useful later on when we talk about ADC, DAC, right? ADC, DAC, because inside the IC that perform ADC and DAC actually is a summing amplifier. So this one is just like you have multiple inputs and then connected to the inverting terminal. So the formula is given here. So I won't go through the detail. Now let's take a look at this example. A few minutes for you to check. So this is a summing amplifier. You have 1 volt here, you have 2 volt here. The feedback resistor is 10K. So the voltage Vout should be minus 10/5 times 2 minus 10/2.5 times 1. So this one is minus 4. This one also minus 4, right? So this one is minus 8. Minus 8. This question is a bit difficult to do, but so imagine you look at this point Vout. I just draw this portion to show to you. So this one is I0, and this Vout, the coming here, this one is 2 kilo ohm, and I call this one is I1. And if you look here, you will see, right? The voltage at this point is 0 volt. And because of the characteristics of the op-amp, the voltage at this point also 0 volt. So from Vout, I go to 10K, I also go to 0 volt, right?
Yes.
I go to 10K. I also go to 0 volt. And I call this point is, for example, I2. So obviously you will see I1 should be Vout over 2K. And Vout is minus 8 over 2K. This one is minus 4 milliampere. So the value is minus doesn't matter, right? It means that actually the current running up, right? But for us, it doesn't matter. That is
So
I1. Yes.
So where is the 8? The 8 is 8 volt where?
Because of this one, so 10 divided by 5 times 2. So you have 2 times 2 is minus 4, right? Because of this, see the summing amplifier RF divided by R1 times V1. Yeah. Then RF divided by R2 times V2. Yeah. So at this point, right? 10 over 5 times 2 is 4. Then 10 divided by 2.5 times 1 This one another 4, so 4. Okay.
Oh, yeah. Yes.
How about oops? How about I2? I2 is V0 divided by 10K, right? So we have
Yes.
minus 8 volt divided by 10K, like minus 0.8 milliampere, right? Now
Yes.
KCL, I0 entering, I1 leaving, I2 leaving, so I1 plus I2. So this one minus 4 minus 0.8 is minus 4.8 milliampere. So the current I0 is minus 4.8. So in the reality, the current is flow like this into the op amp. So this is another example. This one I leave it for you, okay? This one is just like three voltages. 3 voltages. So the way you calculate is the same like what I did just now. Now, this is an example of voltage to current converter, right? So if you have V in here, you need to convert to current. Then you have R1, R2, R3, R4, R5, right? So if you satisfy this condition, then the current is here. So we can convert from V into I. Right, so this is one example. You don't have to memorize this. If this one appear, the formula must be given. Just a simple example. Now let's take a look at this. You read first, okay? You read first. Now you have a sensor. So this one you have a sensor. This sensor provides a voltage from 0 to 1 volt. Now you have to design a V to I converter so that the current you have here is from 0 milliampere to 10 milliampere. Okay. Now let me you take a look a bit. Right. So now what to do? Look at this. The formula for this guy is I equal minus R2 over R1 times R2 V in. Right, so because the minus sign. So the first thing is I will have a inverting buffer. So from 0 volt to 1 volt, I convert to 0 volt, minus 1 volt to 0 volt. So I just flip it, right? So when I have something like this, then when I multiply with minus sign, my current should be positive, right? Okay. So what does that mean? It means that when, for example, when I am 0 volt, I should have 0 milliampere. Obvious, right? When the V in is 0, 0 times something should be 0. Then when this one is minus 1, so when the voltage here is minus 1, so this minus 1 multiply with minus, it should be plus, right? So the minus 1 here will be mapped to 10 milliampere, right? So the way you design is, for example, if you take R1 is the same as R2. So if R1 and R2 is the same, so your current I should be minus V in over R3, right? So when the V in is minus 1, so here you have 1 over R3. And 1 over R3, this one is 10 milliampere, right? Correct? Because V in is minus 1. So from here, your R3 should be 1 volt over 10 milliampere. Right? This one give you 100 ohm. So that is, you have 100 ohm. Right? So what you do is R1, for example, here R, right? R3, you put like 100 ohm there. Correct? And suppose I set R5 and R4. So you see here you have R1 and R2 already are the same. So we have R3 plus R5 is the same as R4, is it? Correct. So if I take R5 is 0, so if this one is 0, meaning I have a wire, then R4 and R3 are the same. So this one also 100 ohm. So if I design the circuit in this way, RR 100 ohm, 100 ohm, I can convert the voltage to a current, and the range is 10 milliampere to 0 milliampere to 10 milliampere. So that is one example. Okay. And let's take a look at the current to voltage. Suppose you have current. Now, this one also quite easy to understand. If you have a current entering this point, the current cannot go inside the op-amp, right? The current must flow here, right? And at this point, it is 0 volt. Then at this point is also 0 volt. So what you have is, you have one end is 0 volt. You have R, you have current I, and then here is your VR. So Ohm law tells you that 0 I times R is 0 minus VR, right? Because the current running in this way. Correct? In other words, VR is minus I times R. So if I have a current I can convert to voltage in this way. So this is one example of current to voltage converter. Right? Now, difference amplifier, I think you have seen this before. I just provide it here for you as a recap. And the difference amplifier, it doesn't have high input impedance. So from there, they can modify this circuit to have instrumentation amplifier. So the instrumentation amplifier, you get these two op-amp, right? To have high input impedances, correct? And if you design in such a way, here is R, and R, and RG here is an external resistor, then the gain is calculated in this way, right? 2R over RG, right? So how to derive, I put it here for you. If you want to go through to as a recap, feel free to do so. Right? Okay. So if you need to have high input impedance for the difference amplifier, you can do this way. Now the op-amp can also be used to build filters, and these are active filters, right? Because this can provide you gain as well. Okay, it can provide you gain. So here's the example of first order active low pass filter and high pass filter. So this one is obvious from the passive filter. This one is low pass filter, right? So this part is doing the filtering, and this part providing you with the gain. Now why? Because can you see, if I forget about this portion, I only look at this, and here I have a V. This one is nothing but just a non-inverting amplifier, right? So for the
Yes.
non-inverting amplifier, the gain is here, right? 1 plus RF over RI, or in this case, R2 over R3. So this portion provides you with the gain, and this portion is doing filtering. Same thing for the high pass filter. This portion give you the gain, and this portion is doing the filtering, right? So that is example. And of course, you can combine low pass and high pass, right, to have this. Okay, now let's do some exercise. Okay, I give you some time to take a look before I go through the detail. So this is a simple example of separating the two stages, right? So imagine if you have a V out here, a V1 here is 0.2 volt, and you want to amplify 0.2 volt. So we have a buffer. Then the voltage at this point should be 0.2. And because this voltage is 0.2, this point also have 0.2. And because here is a wire, so this point also 0.2. And from here to here, it is just inverting the fire. Right? So this one is nothing but your RF. This is nothing but your RI. So the gain should be 500 divided by 50, which is 10. And because this one is inverting, so we have the minus side. Right? So we have like minus 10 times 0.2, it should give you minus 2 volt. So this one is quite obvious. Okay. Now let's look at this. This one is nothing but just a buffer, right? What it is? This one is, oops, non-inverting amplifier. How about this one? This one just summing amplifier, right?
Yes.
Now let's analyze this one first. Vi is 0.1 volt. So this 0.1 volt will come to here. So here you have 0.1 volt. Buffer, this one also 0.1 volt. Right?
Yes.
Okay, so that's how. Now for this guy, it is a non-inverting amplifier. So the formula for VA should be 1 plus 400 over 20 times VI. This one is 1 plus 20 times 0.1. 21 times 0.1, which is 2.1 volt, right? But for those of you who, like, for example, you forget the formula and you don't know what to do, very simple. This point is 0.1. So this point also 0.1, right? And the way we do is here, basically you have VA go down to 400K, go down to 20K. And this point, the voltage at this point is just voltage divider rule, right? 20K over 20K plus 400K times VA. But your V minus here is 0.1. So you can do so, right?
Yeah.
And now when you have this voltage and this voltage, this is a summing amplifier. So just 100 divided by 20 times 2.1. 100 divided by 10 times 0.1. Right? So we will have 100 divided by 10K. So we have 10 times VB is 0.1. And this is 5 times, right? Times 2.1. Right? So this one is
One minus one.
minus 1. This one
One.
is minus 10.5, right?
Mm.
So you have 11. Okay? This one should be 5. So you can write this. Now, let's take a look at this example. This example is where you can, you can change the range. Okay, change the range. So you want to implement a formula. VL is 3.4 V in plus 5. So you not just amplify, right? This one is amplify because again it's 3.5. And at the same time, you move everything to 5 ohm. You move everything by 5 ohm. Right? So not just gain, but you also change the bias. Right? So let's take a look at this. Now we learn the summing amplifier. This one is a summing amplifier. The summing amplifier, the formula is minus RF over R1 times V1 and minus RF over R2 times V2. So the summing amplifier can help us to do the same formula but the minus sign because of the minus sign of the summing amplifier. So in this case, you will see, right? In this case, you will see for V1, I need to have a gain of 3.4. So for example, if I use 34K here and I use 10K here, so the gain is 3.4 times V in. So basically, this portion help me to do minus 3.4 times V in. Agree? Right?
Yes. Yes.
Then suppose I have here is 5 ohm. Then here is 34. Here also 34. So the gain should be 34 over 34 times 5, which is 5 itself. So I have 34, 34. So now I need to have a battery here. Right? A good DC source here. A 5 ohm. Then I have this one. So basically I have minus 3.4 V in minus 5. Now how to get rid of the minus? I need to multiply with minus 1, right? Correct. So the way I do is I use this inverting amplifier. Inverting amplifier. So how come V0 is minus V in? Now, this point is 0 volt, and this point also 0 volt, right? So what you can see is Vi, you go to R, you go to 0 volt, then you go to R, you go to V out. So from here to here, the current here should be Vi over R, this current. Of course, this current must be the same as this current, right? Because they just flow lah. The current flow here must flow here. Cannot go inside the op-amp. So this one should be 0 minus V out over R or minus V out over R. So these are, then V out is minus V in. Correct? Right. So after I have this formula, I use this circuit, then I multiply by 1, right? So I should have 3.4 V in plus 5 lah. Right. So that's how I can use all the op-amp here to help me to do amplification and also to change the level of the voltage. Right. Okay, so that is one example. Now let's take a look at this example. So you need to build a bandpass filter, and the cutoff frequency is 100 Hz and 1 kilo ohm. Sorry, 1 kilohertz. So take note that this cutoff must come from the low pass filter, right?
Yes.
And this cutoff must come from the high pass filter. So it's in the band pass filter, it doesn't mean that the high pass filter should have higher cutoff frequency. Hey, by the way, what happens if the high pass filter has higher cutoff frequency? Suppose low pass filter here, high pass filter here. Suppose this one F1, this one F2, and F2 is more than F1. Very simple. Imagine you have all frequency here. Entering here, all frequency. So at this point, right? Here's F1, here's F2. At this point, because this is a low pass filter, so it's only keep the low frequency. And it keep until when? It keep until F1. So basically, you only have this at this point. And if you pass a signal through the high pass filter, what does it mean by the high pass filter? It only allows high frequency to pass through. How high? More than F2. But look, more than F2, it has nothing, right? And this portion, the high pass filter will remove. So if you do so, you theoretically, you have no frequency, right? So if the cutoff frequency of the high pass filter is more than the cutoff frequency of low pass filter, when you combine them like this, theoretically, you have nothing here, right? Okay. So if you have the cutoff frequency of 100 Hz and 1 kilohertz, and this is a bandpass filter, then this is a frequency response. You have 100 Hz here, 1 kilohertz here. This is a top, and here is you go down by 3 dB from the top, right? Now, this gain is 10 dB. And your signal has 1 volt VPP, 100 Hz. So where 100 Hz? Here, right? Here, 100 Hz. So 100 Hz is in the pass band. So this frequency, right? So for sure, now this one frequency is 500 Hz. VPP in is 1 volt. Of course, the output frequency must be 500 Hz. But what is VPP out? Or to make it simple, V in, VPP is as well, right? Okay. So this one is quite simple, because if the gain is 10 dB, and how to have this 10 dB is 20 log base 10 of the normal gain, right? Correct? Gain in dB is calculated as 20 times log base 10 of the normal gain. So here 20, here 20, here 10. So log base 10 of A should be 10 over 20 should be 0.5. And A should be 10 to the power of 0.5. Can you help me? What is 10 to the power of 0.5?
3.16.
3.16. So from here you will see V out should be V in times 3.16. So you have 3.16 VP prime. Now, what 10 kilohertz. So if my input frequency is 10 kilohertz, V in is 1 V, should be the output. Anyone can tell me what should be the voltage of the output? Amplitude of the output. The passband is only from up to 10 kilo ohms. So 10 kilohertz is very far away in the stop band. So basically, this one is theoretically, this one is almost 0 volt. Of course, it cannot be exact 0 volt, but it's very small. Right? So 10 kilohertz is in the stop band. So the filter will remove this 10 kilohertz. Does it make sense? Right? Now, let's do this exercise. So you have filter 1 and you have filter 2. Now filter 1, low pass or high pass?
Low pass.
This one should be high pass, right?
Yes.
Now, this one is just a buffer, right? So the gain here is 1. Gain here also 1 because of the buffer. Okay? If you have like this, then you can have a gain, right? If you link directly like this, and this one is just a buffer, so there's no gain. Okay. So of course, first order, right? The order here is first order. And you have first order low pass filter on top, and at the bottom you have first order filter. Okay. Now the cutoff frequency for this one I call F1 is 1 over 2 pi. R is 20, 10, 3. Okay, let me write down. F1 is, let me see. F1 is 1 over 2 pi 20k. C is 22 10 minus 9. So this one should be (361.7 Hertz). So this is the cutoff frequency of the low-pass filter, right? The low-pass filter cutoff frequency is here. For the high-pass filter, the cutoff frequency is 1 over 2 pi 27 3 56 and 9. So and 5 3. So for the low-pass filter, it should be like this, right? Sorry, low-pass filter should be like this. And because this one is gain in dB, this is again in dB, and because gain is 1 dB is 0. So this one is -3, and at -3, you should have 361.7. This one is frequency in hertz, right? For the high-pass filter, it should be something like this, right? So again, this one is 0 dB, and when you bring down to -3 dB, this point is 3 dB, this one is 0. Okay, let me, this one is 1.0.3. Okay. So for the high pass, should be like this. This one is gain in dB, and this one should be 0 dB, and you bring down to -3. This one should be 105.3, and here frequency is something like this. Right? So this is the frequency response of the low pass filter, and this is a frequency response of the high pass filter.
Mm.
Now, if they say, oh, you have to draw us how to have the bandpass filter based on these two filter, what you can do is you can just combine, right?
Mm.
And you can have something like this. By the way, whether you draw the low pass first or high pass first, it doesn't matter. It doesn't matter because imagine if this one is low pass first, then you go to high pass. So suppose at this point you have O frequency, then because of the low pass filter, the cutoff frequency is 300, right? So you still have up to about 300, for example, 300. Then the high pass will remove everything below 105. So at the end, you have 105 and 361. But imagine if you have a high pass filter first, followed by a low pass filter. Now, so here you have O frequency. High pass filter, but high pass filter will remove everything below 105. So you have everything here. But the low pass filter only keep up to 361. So in the end, you still have 105 to 361. So the order, it doesn't matter. The order doesn't matter. As long as the the cutoff frequency of low pass filter is higher than the cutoff frequency of the high pass filter, then the order doesn't matter. So when you combine them like this, actually you can have a bandpass filter, and this is an active one, right? It's active one. And by the way, the gain here is 1, and the gain here is also 1. But suppose if you desire to have some gain here, you desire to have this gain, and you have another gain here. So for example, this one you desire to have like 10 times. This gain is like 10 times. By having a resistor, right? By having some resistor. So for example, you have a resistor here, right? So you have a resistor here, and resistor here. And suppose this gain is 5 times. And suppose this gain is 10 times. What is the total gain?
50.
Yeah, so it should be 5 times. Okay, so take note of that. But so you take note of these few questions about filter. Okay, then the quiz will ask you something similar to this. So the quiz next week, you have the reliability part and also the simple filtering like this. Okay. Any questions?
No, sir.
Yeah. Okay. So if not, then I will see you next week.
Sir, I want
Yes.
to know our exam date is 26 February, right?
I have no idea. I have to check again.
Oh.
But in your step is already there.
No, not yet.
Because I haven't seen the email regarding the date.